Hi everyone. Today we're going to talk about the mean value theorem for integrals as well as average value. So if you think back to what you've learned so far about finding area under a curve, remember that area under a curve was underestimated most of the time. When we used inscribed rectangles, it produced a negative error, but it was overestimated, the area was overestimated, when we use circumscribed rectangles that jutted out beyond the curve, and that yielded us a positive error. What the mean value theorem for integrals states is that somewhere between these two scenarios of an underestimation and overestimation, there should lie a single rectangle whose area will precisely equal that of the region under the curve, as given to us by the definite integral. Now, yes, if you've heard this phrase mean value theorem before, you're not imagining it. You learned the mean value theorem back in differential calculus. Remember that if a function f is continuous on the closed interval from a to b, and if it's differentiable on the open interval from a to b, then there will exist, remember the backwards e means there exists, a c value in the interval from a to b such that f prime of c will equal f of b minus f of a all over b minus a. So hopefully you recall really how this translated into real life and applications was that what this is guaranteeing us is the existence of a place where the instantaneous rate of change will equal the average rate of change. And hopefully you remember that the C value that you can find is not necessarily unique. There can be more than one. And this is an example of an existence theorem, as we call it in mathematics. This simply tells us that something exists. Now, granted, the formula kind of gives us a little hint as to go about how to find this C value, but otherwise it really just tells us that the C value does exist. So that brings us now to the mean value theorem for integrals. So now if a function f is continuous on the closed interval, then there exists a c value in the closed interval from a to b such that the value of the definite integral of f of x from a to b is going to equal f of c times the quantity b minus a. Now think about what that tells us. The definite integral, remember, gives us the area under the curve, the exact area under the curve. F of c minus times b minus a is giving us the area of that single rectangle that we will be able to find, whose area will be equivalent to the actual area under the curve. F of c is going to be the height of the rectangle. B minus a gives us the width of the rectangle. Once again, C is not necessarily unique. There can be more than one answer for C, and once again, it is an existence theorem, just like the original mean value theorem was. So let's take a look at this graphically. What this means is that if you look at the curve, right, the area under the curve that we would be finding would be all of this area here. Okay. What this is saying is that we can find an area of a rectangle whose area will be equivalent to that. And you can see the grayed shaded rectangle. The width is going to be b minus a. The height of the rectangle, see, it's always going to be, the height is always going to be dictated where the top of the rectangle hits the curve, and that's really where the f of c comes from, because c is going to be the x value at which that height occurs. So that's why we find f of c to give us the height. So let's take a look at a couple of example problems. Suppose we want to find the value of c that satisfies the mean value theorem for integrals on the interval from 1 to 3 if our function is simply x squared. So let's go ahead and just set it up, and then we'll walk through it. So we're finding the integral from 1 to 3 of x squared dx. And according to the mean value theorem for integrals, that area, that definite integral, should be equivalent to the area of a rectangle given to us by the width of the rectangle, which we'll get by doing 3 minus 1. So this is your width. And your height is going to be f of c. Okay? So we can evaluate this definite integral just to make it a little bit easier. Let's just go ahead and do that on our calculator. So remember, we can do math 9 for a definite integral, and we want the integral from 1 to 3. And I'll just go ahead and type in x squared here to make it easier instead of putting it under y equals. So that gives us 8.6 repeating, which it might be easier to use that as a fraction. So let's go ahead and express it as a fraction. 26 over 3. So let's use it that way. So we have 26 over 3. 3 minus 1, of course, is 2. So if we start solving for f of c, we can divide both sides by 2, so that gives us 26 over 6. So that's equal to f of c. But remember, we want to find what c equals. So it might be helpful f of c, of course, we know is going to be given to us by the function. Now you can just call it c squared if you wish, or if you find it easier to call it x squared and then just express your answer as c at the end, that's fine. So we know that in order to solve for x, we have to take the square root of both sides. So x is going to be the positive or negative square root, and I'm going to go ahead and reduce that fraction. So that's what I get for x. But remember that, according to the theorem, the desired c value needs to lie in between 1 and 3. So we can't have the negative as our answer. So our c value would have to equal the positive 13 over 3. Or if you prefer a decimal, that's fine. It comes out approximately 2.082. All right, so let's draw a picture of what this would look like so you can get a better visualization of it, of what we just did. Let's see how good of a picture I can draw. So I need an x squared graph. There's 10. Okay, so if I start graphing this, so obviously it's going to be a parabola, hopefully a somewhat decent one. All right, and what I was trying to find was the area under the curve in between 1 and 3. All right, so what I was trying to find was this area here. So what the mean value theorem for integrals tells us is that yellow area should be the same as the area of a single rectangle. Now remember, we found the c value to be approximately 2.082, so just a hair above 2. So where the c value comes in is maybe like right around here. All right, so what the mean value theorem is saying is if we were to create a rectangle, all right, so the left side of the rectangle would be at 1, the right side of the rectangle is going to be at 3, the base is obviously the x-axis. The height, if we trace up and it hits about there, if my drawing's at all right. And if we just make a rectangle out of this, the area of that orange rectangle should be equivalent to the yellow shaded area under the curve. All right, and if you take a close look at it, and if I all drew this somewhat well, what you should notice is, you see this positive arrow right there? Kind of looks like it's jutting out beyond the curve. That area should basically offset that area. All right. Might not be perfect the way I drew it, but that's the idea. All right, and that's really what the mean value theorem for integrals does. It's an interesting idea, just saying that you should be able to get the area under a curve by finding a rectangle whose area is going to be equivalent to that definite integral, giving us the exact area under the curve. All right, let's try another one. I think I have a trig function for us next. So same instructions. Now we want to find the value of c satisfying the mean value theorem for integrals on the interval from 0 to pi if f of x equals sine of x. All right, so we're going to set it up, the integral from 0 to pi of sine of x dx. And according to the mean value theorem, remember we're talking about the area of a rectangle, so the width of the rectangle will be given to us by pi minus 0. Okay, so this is the width. Remember, the height is given to us by f of c. All right, so let's go ahead and evaluate that definite integral on our calculators. So we're doing the integral from 0 to pi of sine of x dx. I think I need another parenthesis. There we go. All right, so hopefully everybody got 2. All right, so that's just equivalent to 2. So pi minus 0 is obviously pi. So if we divide both sides by pi, and we'll just leave it like that for now. We might want to get a decimal answer after. So remember, we're trying to solve for c. So in order to find c, we might need to think of this as a sine of x. All right, so since we're trying to solve for x at this point, that's an inverse sine that we need to do. Because we know the sine value, we need to find the x, the angle. So you need to remember that our answer needs to lie in between 0 and pi. If we think about the unit circle, all right, remember 0 is obviously over here, pi is over here. So if we're talking about from here to here, remember sine is going to be a positive both of these quadrants. So this is a case in which we are going to have 2 answers. So when we do inverse sine initially on our calculators, remember that's going to give us the first quadrant answer. The second quadrant answer we'll have to get by taking that reference angle and subtracting it from pi. All right, so we can go ahead and walk through that. Clear this out. So we're going to do inverse sine of pi over 2 over pi. And hopefully everybody gets about 0.690. So remember that's radians. You should be in radian mode on your calculator. So that's your first quadrant answer. All right, remember the second quadrant answer, this 0.69 now serves as our reference angle. So if we do pi minus that, go copy that. There's your second answer, 2.451. So this is a case in which, remember we were saying that the value of c that you will find is not necessarily unique. This is a case of that, in which we do have 2 answers for c. All right, so our answers for c then is that it can be 0.69. All right, that's radians, if you care to designate it as radians. or 2.451 readings. All right, so let's take a look at what that looks like. So let's draw ourselves a sine curve. So we only need up to pi, so let's just worry about that. So here would be like pi over 2. Remember, sine of 0 is going to be 0. Sine of pi is going to be 0 as well. Sine of pi over 2 is going to be 1. So let me put that up there. Basically, this part kind of looks like a semicircle. Okay, so remember what the mean value theorem for integrals tells us is that if we want to find this shaded area, this is the shaded area that was given to us by that definite integral, we should be able to find a rectangle which is going to start at 0 and go over to pi. That's going to be the width. And what we just found was that 0.69 is the first value, so that comes in right around, I think it's around here, because I know pi over 2, that's going to be 1.59 or so. So that's going to be right around here. So this is like C1, okay? The other one that we found, the 2.451, that kind of comes in right around here. That's your C2. So because of the symmetrical properties, really what happens is, as I draw this rectangle, notice how, if I drew it well enough, notice how it's hitting, there's C2, there's C1. All right, so the area of that orange rectangle should be equivalent to the yellow area under the curve. All right, so now that you've learned about the mean value theorem for integrals, this brings us to a very related idea, that of average value. The value of f of c that we just talked about with the mean value theorem for integrals. Remember, f of c gives us the height of that desired rectangle. That is what we refer to as the average value of f on the interval from a to b. One thing to take note of, just because it says average value, it does not necessarily mean it is the average, in other words, the arithmetic mean of f of a and f of b. A lot of people think you can just add together f of a plus f of b and divide by 2. No, you cannot do that. All right, it's really representative of the height of the rectangle. So by definition, the average value is really that definite integral multiplied by 1 over b minus a. All right, if you think about it, let's go back a few slides to the actual formula for the mean value theorem for integrals. All right, what you're really doing now is you're trying to solve for your average value is this part right here. That's what you're trying to solve for. So you can really think of it as dividing both sides of the equal sign by the quantity b minus a. Right? That's where the average value formula comes from. A lot of people just prefer to set up your problems using this mean value theorem for integrals and then just solve for f of c. Now, if you think about how we work through these other problems, you've actually found the average value. Right here, where we got to this point, where we said f of c was 26 over 6. 26 over 6 is your average value. That's the height of the rectangle. All right, in the sine problem we did, right when we got to this step, the 2 over pi is your average value. That is the height of the rectangle, your f of c. All right, that's all that average value is really specifically finding the height of the rectangle. So how you set it up is really up to you. You can use this formula here. Again, though, a lot of people, as I mentioned, just prefer to set it up as the basic mean value theorem for integrals and just solve for f of c and just kind of stop the problem at that point. All right, you really can do it either way. There is a graphing calculator program that you have called AvgValue. Looks like AvgValue under your programs. So I will walk you through that as well as we do an example problem. So let's try this one. We want the average value of the function 3x squared minus 2x on the interval from 1 to 4. So why don't we just set it up like the normal mean value theorem for integrals, and then once we get to that line where we have f of c equals something, that's pretty much where we're done. Okay, that will give us the average value. All right, so remember we want to set it up the integral from 1 to 4 of 3x squared minus 2x dx. And remember, according to the mean value theorem for integrals, that's going to be equivalent to the area of the rectangle, the width of which is going to be given to us by 4 minus 1, and the height, your average value, will be f of c. So let's go ahead and do that integral on our calculator. And again, I'll just type the integrand in here directly. So hopefully everybody got 48. So we have 48 equals 3 times f of c. So divide both sides by 3, you get 16. All right, so this is your average value. That is really the height of the rectangle. Now, another question that you're often asked is, where does the average value occur? If that's the case, well then that pretty much just amounts to finding C. All right, because we know the average value is 16. That's equivalent to f of c, which is really the function. So we can just go ahead and solve that. We have a couple different options for solving it. We can solve it graphically. Let y1 equal 16, let y2 equal 3x squared minus 2x. Another option, bring the 16 over. So you have a quadratic equal to 0. Then you could run the quadratic formula on your calculator, or you could factor it. Either one. Why don't we just go ahead and use the quadratic formula. So a would be 3, b would be negative 2, and c would be negative 16. So we get as our answers a negative 2 and 2.6 repeating, which is 8/3. Now remember that these would be the two values that we get. All right, so we get the x values, and it's 8/3. That's the decimal we got. But remember, it has to be in the interval from 1 to 4. So really the only one that is where this particular average value occurs would be 8/3. All right, so really an average value problem really is involving the mean value theorem for integrals, because the average value is the same as the height of your rectangle, and the answer to the question as to where the average value occurs is simply that C value, whose existence is guaranteed by the mean value theorem for integrals. As you do these problems, you definitely want to take care to notice what exactly is being asked of you, whether it's the average value or for where the average value occurs. These often will show up in the multiple choice on the AP exam, so make sure you're answering the correct question. All right, so let's maybe get a visual of this. I think I left room to draw it. We know it's going to be a quadratic, and then I'll show you how to use that average value program on your calculator. So I know when x equals 4, the y value is way up here at 40. I do know that. Let's see, I know when it was 0, 0. There's some other points. But basically it's going to be, see if I can freehand this at all pretty well. It's going to be a quadratic, obviously, a parabola, part of a parabola. So it kind of looks like that. So according to, the definite integral we had set up, really we were trying to find this area here. All right, so the average value we found tells us the height of that rectangle. Remember, that was 16. The C value we got, remember that was 8/3, 2.6 repeating. So that would be right about here-ish. All right, so remember if we trace this up to the curve and create a rectangle out of it, the area of that orange rectangle should be equivalent to the yellow area under the curve. All right, so this height of the rectangle, that's 16. That's your average value. So let me show you how to run the program. So let's go back to the calculator. What you'll need to do is have the function under y equals. So the 3x squared minus 2x and I'm just going to go ahead and zoom 6 to graph it first just to get a look at it. Obviously we know it's going to be a parabola. Okay. So when you run the average value program, go back to your quit screen, bring up program. Remember your programs will be alphabetized. Yours might be a little different than mine because I have some other extra programs in here. You want the one for average val. Average val is what it looks like. All right, so when you run the program, it's going to ask you for the endpoints. Now, please take note, it does ask you for B first. Just FYI. So that would be 4 in this case. A was 1. All right, what it does then is it pretty much goes to your window and it's going to draw the curve for you. If you take a look at your calculator screen, the far left part of your screen in this case would be x equals 1. The far right would be x equals 4. All right, so pretty much everything in your window is basically in between the A and the B values. All right, now you might notice in the upper right corner of your calculator that it's still working and thinking. Hit enter again. It's going to draw a horizontal line, and that horizontal line is indicating the top of the rectangle. So basically what the calculator's done is it's created your screen to be the rectangle. All right, so the bottom of your screen is like the bottom of the rectangle. The left of your actual screen is the left side of the rectangle, and the right side of your screen is the right side of the rectangle. And then the line coming across in the middle somewhere, that's the top of your rectangle. So it really is drawing the picture just like we've done. It's only focusing in on those A to B values though. All right, now you might notice in the upper right corner again, your calculator's still thinking. Hit enter once again, and it will tell you what that average value is. Now notice it's only giving you the average value. It will not tell you where it occurs. Okay. One thing to take note of is that when you're done using this program and you want to graph something else, this part's really important. Please don't forget. Part of the program, in order to get the picture to look like this on our screen, is it needs to wipe out your x and y axes. Okay, so if you wanted to now go graph something else, you need to remember to turn those axes back on. All right, the way in which you do that, it's if you notice over your zoom button, it says format. So if you do second zoom, and you'll notice that and again, depending on the calculator, you might have different a setup than I do, but you're looking for a line that says like axes on, axes off. If you look at mine, it's this one here where it says axes then colon. See how it's set to off? I need to turn that back on. All right, so again, depending upon, there we go. Now it's on, and I can even change. All right, I want my axes to be black. You know, this is for the TI-84C, the color one. If you have a regular TI-83 or a TI-84, it probably just says axes on, axes off. Okay, but it is under second zoom, and that's just something you're going to remember to have to do. All right, so that walks you through the mean value theorem for integrals as well as average value.